All right, so shall we move to what Rahul was asking? Okay. Okay, so Rahul was asking about how do we show that SU2, the manifold of SU2 is a three-sphere. And let me just find.
I was hoping like you could like clarify the physics of it, like why, the concept behind why we are doing what we're doing mathematically. That part is not clear. It may be a very simple thing, but I don't understand it.
Yeah, so I think, it's better if I do it in a simpler setting. Let's take, say, U1. Okay, what is U1? It's the group of phases under multiplication. Right, so if I take, so phi is initially, I take it to be a real number. Okay, so then this is phase, right, Rahul?
Yeah.
So, but, we know that, if I take phi and take phi plus 2 pi, then e to the power I phi does not change, right? Because then we just multiplied by 2 pi I, and this is 1. Right, so we should identify this with this plus 2 pi. Right, because otherwise we are not using our parameter space is actually not this thing, but it's this thing up to this identification. Does that make sense?
Yes.
So let's look at it geometrically. So this is, say, R. This is the origin. And as we come to 2 pi, we say that, well, 2 pi is, I'm going to call it the same point as 0. And if I had gone to, say, 4 pi, that would also be equal to 0 or 2 pi. So at every 2 pi, so if I take R and identify every point at 2 pi distance, sorry, this is 4 pi. Then what do we have? So suppose that Rahul is walking along in this direction, and you want to get to, say, 4 pi, but you can't, because as soon as you reach 2 pi, you're back at this point. So this space is actually not the real line. This space is actually a circle. Right. Whereas, this point is both 0 and 2 pi.
Sir, you discussed this in the other class, so I was confused about it. So after I thought kind of about it, so I think it's, instead of a circle, it's kind of a rose petal leaf. So in each of the petals, that's one equivalence class, and depending on how many numbers you basically divide it, that's the number of the petals. I think instead of a circle, you get like many circles having one intersection. Is that a correct interpretation of it?
I'm not exactly sure what the geometry, you said rose petals, right? So you basically are
having
saying
one
that
intersectioning point. Yeah. That's
yeah, but
like
all
R divided
no,
up by Z.
Yeah, I mean, it's the equivalent thing. It's the same thing. You're saying that this petal is, but what I'm saying is this petal is identified with this petal, and this petal is identified with this petal. And let me explain why this picture although it's correct, it doesn't give a manifold structure, right? So let me,
Yeah,
of course,
at the
there's
center there is an ambiguity. It's not
exactly.
like-
So there are an infinite number of petals, but we can only take a subset, and that's fine. And we see that in the neighborhood of this point where you identify, it's not a manifold anymore because it's not locally Rn. It's not locally R1. Whereas this thing is locally R1. At any point, it looks like R1 around in the neighborhood of any point. Okay, Rahul, but is it clear what we're doing here?
Yes, sir.
Okay, so this is actually interesting because now let's apply. Let's apply, say, let's take e to the power I don't know, what is 90 degrees? Pi by 2, right? And let's take e to the power I, say pi by 4. Okay, so this is 90 degrees, this is 90 degrees, and this is 45 degrees, right? So now, let me draw my circle. I'm just drawing it, embedding it in a higher dimension. So this point, the first point is over here. And so this is, say, a G1. And this is G2. So this is G1, and this is G2. Now, if I multiply these two guys together, G1 times G2, I get e to the power I pi by 2 plus I pi by 4, which is e to the power I 4, 3 pi, right? 3 pi by 4, right?
Yeah.
So that means that if I multiply these two things, I end up at this point. This is G1, G2. But this is actually an abelian group because, as you can see, it doesn't matter if you multiply G1, the order of multiplication doesn't matter, right? You get to the same point.
Yeah.
Okay, so this is how, by multiplying group elements, you're actually moving on this manifold. It's a very nice thing. By multiplying these group elements, you're actually moving around on this manifold. Okay. And one way of thinking about the inverse element is that if you take G2 inverse, it just moves you back in the opposite direction. Okay, this is basically how we think of it physically or geometrically. So similar thing you can show in for SU2. So I think probably it's clear to Rahul that, if I take the parameter space of a matrix in SU2, it's, if I write U as alpha 1 plus, say, beta is a set of 3 numbers. So this is SU2 as far as long as alpha squared plus beta mod squared is 1. This is another representation of SU2. I think that was part of one of the exam questions, right?
Yeah.
Yeah. So, this is a very nice, I could have said, okay, I can write this as e to the power I theta dot sigma, right? But this does not, make it clear that it's a 3-sphere, whereas this does, because beta has 3 components, beta 1 plus beta 2, beta 1, beta 2, beta 3, and then beta dot beta is just beta 1 squared, beta 2 squared, beta 3 squared. So this equation is alpha squared plus beta 1 squared plus beta 2 squared plus beta 3 squared equals to 1. This is the equation of a three-dimensional sphere,
Right.
right?
Yeah.
So, so I think you understand that it's a three-dimensional sphere. But what we now want to see is that how does it correspond geometrically? That's what you want to do. And we can do something similar. So a three-dimensional sphere, suppose, has a North Pole. So this is the North Pole. And suppose that we have chosen our parameters in such a way that all the angles, theta, are 0 at North Pole. Sorry. At the North Pole. So that means that the North Pole is also the identity element, right? So this is here, a little dirty secret of Lie group comes out, which is that depending on your parameterization, any point can be the identity element, okay? And, so anyway, but that's a separate issue. And it has to do with the fact that these manifolds that represent Lie groups are very nice, symmetric, they have a lot of symmetries. So for example, S3 is what is known as a maximally symmetric space in 3 dimensions. In 3 dimensions, a three-dimensional manifold cannot have more symmetries than the symmetries that S3 has. Other three-dimensional manifolds which have the same amount of symmetries are R3 and the three-dimensional hyperboloid. So these are the three. These three are called maximally symmetric spaces when the signature is plus, plus, plus. If the signature, if there's a time component, then you have, these things are replaced by S3 becomes what is known as a three-dimensional de Sitter space. R3 becomes the three-dimensional Minkowski space. H3 becomes the three-dimensional anti-de Sitter space. Anyway, those are physics things, so that we won't go into, but let me just, so this would be the signature of these guys, and the signature of these guys would be like this. Okay, what is signature? Signature means that there is a metric tensor whose signs of the diagonal are like this and like this. Okay, so let's get back to thinking of the geometry. So now let's take only theta 3 to be non-zero. And then, apply that exponentiation. So if I do this exponentiation, then at some point, I have tau 3. So this is going to give me a matrix e to the power I, theta 3 by 2, e to the power minus I, theta 3 by 2. Okay. So depending on so theta 3 would be some angle subtended at the center, which is kind of outside the, this is theta 3. So then, this element would be represented by the end of this arc. Let me use a different picture. This end of this arc that we traveled on. Okay. So this is going to be, this point is going to be e to the power I, theta 3, tau 3. So depending on different values of theta, you can travel to different points on this 3-sphere. Every point on this 3-sphere is going to be representing a matrix through this parameterization. Okay. So is this a bit clearer, Rahul, or do you have more questions? Just like,
Yeah, this is, yeah, it's better.
Okay. So, these things are really amazing. Groups are really amazing. So for example, you can actually generate some curves, natural curves on a group. Suppose you start at some point, given some point G on the group. So, you have some group and this is G. And you have another group element which has some parameter theta. And you multiply these two. Okay, you multiply these two, and theta takes value in some range, right? That range could be like a compact or non-compact. I don't care at this point. But as you vary theta, what happens is that you trace out a curve. So, there are many very nice ways of and if you go long, you might actually end up in the same place. But that's beside the point. So groups have all these very nice properties that just by applying them, we can generate curves on manifolds. And at some point, we will explore those meanings, okay? When we come to the geometry of Lie groups and their application to a differential geometry. I will do that.
Sure.
Yeah.
I have a question. So you are talking about S3.
So sorry to interrupt, but Nahi, I think there's going to be a namaz very soon. When would you like to go on the break?
6:15.
Okay, so let's talk till 6:15 and then we'll take a short break, okay? Okay, yeah, sorry, Asai, for interrupting you.
Oh, no problem. I was going to ask, we're talking about S3, but what you've drawn here is S2, right? Like this is a two-dimensional sphere.
Yeah, I'm not able to draw S3, unfortunately.
Okay, I was just confused about that. Which one was S3?
Yeah. And I think it's worthwhile to go through this again. The geometry, because this is a very exotic geometry. And this is very, it's a completely regular geometry, but it's something that we don't usually think about, It's not a simply connected space. Right. So the most, what is a simply connected space is a simply connected space, or let's say manifold, because that's what we're discussing, is a manifold where every circle can be continuously shrunk to, 0, to a point. Right? So, and we know that whenever we have a sphere, we can have some closed curve, and that curve we should be able to, like a very stiff rubber band, if you let it go, it'll just, become like a point, right? So spheres are simply connected. What else is simply connected? R3 is simply connected, right? We live in R3. We know it's simply connected. Right, so, but this thing, SO3 is not simply connected. And the reason is that because we constructed this this isomorphism, and we saw that both U and minus U maps to the same element in SO3. So that means that geometrically what we're doing on the SO3, on S3, is that we are identifying all antipodal points. So if we identify all antipodal points on S3, then we get SO3, right? So this is identification. But now if I want to draw this identified, so what I can say is that, okay, the northern hemisphere, so by the way, but for a three sphere, the equator itself is a 2-sphere, right? So we can represent the 3-sphere under this identification just as the northern hemisphere, right? Because all the points in the southern hemisphere are now being represented by the northern hemisphere. But those points which were on the equator, they are still oppositely identified, right? Because we cannot get rid of the equator, otherwise our space won't have a boundary. Right? So the points on the northern, on the disk, inside the disk, you know, they are simple points. They don't have any you know, complicated features. But the ones on the S2, on the edge of the disk, they are oppositely identified. So if I ignore now the geometry, I can just flatten this space, right? So I'm ignoring the geometry, I'm just looking at the topology. So I can draw it as a disk. So this is this is S2, and this is some interior. But it's not any simple S2, it's S2 over Z2, right? It's S2 with the opposite points identified. So this is just identification. So let's keep that in mind. I'm gonna.
Sir, এটা কি S2 হবে নাকি D2 হবে? Because
The
like মাঝখানে
yeah,
তো
yeah, the
points
edge,
আছে।
yeah, the edge is S2, sorry. The edge is S2, and the inside is basically the interior of D3. Of D3.
তাহলে কি স্যার মানে স্পেসটা D2 over Z2 এরকম হবে না?
No, I don't know what we want to call it, but you know, this is it's not a simple disk. It's probably what is known as a projective disk or something like that. Yeah.
Projective.
Yeah, this is like some version of RP. It has a name, but I forget. So the interior is not S2. The interior is the interior of D3. If the boundary was just S2, then it would be a D3. So you might say it's D3 with the boundary having some Z2 identification. Okay, some complicated version of D3. Let's call it D3 tilde. Okay, so now if I take, say, you know, a curve which goes like this, then this curve cannot be. My first question is it a closed curve? Is it a loop?
Yes, yes.
What about Saif?
Yeah, it's a closed curve.
Rahul?
Yeah, okay. It is.
Is it clear to you that it's a closed curve?
Not entirely, but
Okay. No, that's fine. You know, I'm going to explain why it is a closed curve. So what is a closed curve? A closed curve is something where if you travel in one direction, you come back to the same point, right?
yeah.
So, by the way, welcome, Shujosh. I had noticed you had come in. So if you travel in this direction, as you reach this point, because of the identification, you end up here, right? And as you travel, you come back to the same point. So it is a closed curve in that sense, right?
Oh, okay.
You never had to double back. You never had to go backwards, right? You're always going forward, not exactly in the same direction, but never turning back on this curve, right?
Yeah.
So now suppose now on a sphere, on a regular sphere, if we have a closed curve, we can shrink the closed curve gradually until it becomes a point, right? And that is what we call a simply, because we can do that on a sphere, that's why we call the sphere a simply connected manifold. Let's try to do that over here for this curve. So if you want to shrink this, what can we do? So we can, we can do this. We can pinch it off, but that's not going to be, then we just have a self-intersecting curve. We are not really we still have a portion which is not getting smaller. Another thing we can try is that we can bring this point to this point. So we can start moving this point in this direction. But because opposite points are identified, this point then starts moving in the opposite direction. Okay, so we get this really weird thing where you can't really catch yourself because these 2 points are the same points. So this curve, it turns out, cannot be shrunk to a point. Okay, so here we have an example of a curve which cannot be shrunk to a loop, shrunk to a single point. But there's another kind of curve. So we also, of course, have this curve. This curve can always be shrunk to a point. But we have another curve which say, comes out of this point, goes here, but this point is this point, comes out here, but this point has an antipodal point here, goes over here, right? So this is another curve. Let me just highlight this. This is also a closed curve. But this closed curve can be shrunk to a point because this point can be moved to this point. If you move this point to this point goes to this point. And then you can just, when these 2 points are the same, you just have this thing, right? And then it can be shrunk to a point. So this means that, there are 2 kinds of loops in this manifold. One which can be shrunk to a point, and one which cannot be shrunk to a point. So that means that SO3, which is an S3 over Z2, also known as SU2 over Z2, is not a simply connected manifold. Okay, and so let's take a break, and when we come back, let's take 15 minutes, right? So let's meet back here at 6:30. When we come back, I'll give you even a more simple example of a non-simply connected manifold, okay?